Greetings to all dear judges. I, Jain Dadich, leader of Team Rockmongus, is so much excited to present our project Cosmic Trebuchet. Let me first introduce a team member. So first is myself, Jayant Dadich, then Devarki Banerjee, then Satvik Sumant, then Arun Karthik GR. We at Rockmongus have come up with an idea to serve the rocket industry. So this will be our flow of presentation. First is introduction, then construction, then course, and then finally solution. The idea which we propose has been in existence since 1966, popularly known as Skyhook, which was just a theory. In 2007, European Space Agency, in collaboration with students and universities, established a team, Young Engineer Satellites, 2 of 450 students test Tether-based solution in deployment and recovery of satellite. The problems currently faced by industry are of it being expensive and inability to carry large payloads. Now coming to the construction part, for the construction of Space-Tether launch system, we will be requiring the parts mentioned on the screen. So for hardware requirements, first it will be fuel tanks, engines, it will be either chemical or iron, then control modules, solar panels, and the last is cables. And for software requirement, definitely it will be AI-based control softwares. Starting with fuel tanks. The fuel tanks will serve as the counterweight for our spinning tether system, having 2 fuel tanks of 3-meter diameter and length 7 meter each. Will make the counterweight around 30 tons without fuel and suitable to balance out the forces while spinning. Now, Devargi will continue.
Hello, this is Devar here. I will be explaining the following parts. Engines. Engines are the most vital part of our mission as they are used for station keeping of tether system and creating the spin for launch of spacecrafts from it. We would need around 6 to 8 ion engines for this mission, in which 4 are used for station keeping purposes of the space trebuchet and 4 more engines will be required to spin the tether with 2 engines on either side of the docking port to get clock and counterclock spin. We plan to use commercially available Hall effect ion engines with specific impulse of 1600 seconds and a thrust of 1.5 Newton. The engines used for spinning can also be attached with chemical engines for a faster spin of tether. Now next, coming to control module and solar panels. The function of control module will be in controlling the refueling of incoming spacecrafts, calculating and executing the spins, and docking controls. The solar panels besides provides the power for control module and will also be capable of folding themselves in order to prevent them from getting shredded by the forces created by the spin. Thank you. Now over to Satvik.
Hello, this is Satvik. I'll be explaining the following aspects of our ideas. Cables are the most crucial part of our system, for which there are a few commercially available material which can be used to make the cables appropriate for our mission, such as the Dynama fiber, Spectra fiber, carbon fiber, and in upcoming future, carbon nanotube fibers also. These fibers are used for heavy duty applications in industries and even in bulletproof jackets. These fibers are capable of providing the flexibility for the spin, but are not rigid enough to support the forces created by approaching spacecraft. If we make a composite material of these fibers with aluminium, then we will be having a rigid cable to support all the forces created in the spin and also in the docking and refueling of the spacecraft. The cable made from these material and aluminium will also work as a refueling rod such that when required, the spacecrafts can be refueled for further missions. In this illustrative design, we see that there is a counterweight on the bottom and a docking port on the top. All sides of the counterweights have been attached with engines so that we can use them for station keeping purposes. And the docking port is also having engines on its either sides to provide the spin in the clockwise and counterclockwise direction as per the mission, for which the velocities and orbital trajectories will be pre-calculated. The software requirement for this mission are all custom softwares, which will be artificially intelligent softwares so that no human error can interfere in the success of our missions. Thank you. And from now on, Arun will be explaining further aspects of our project. Thank you.
Hello, this is Arun. I'll be talking about cost and other aspects of our mission. Based on the cost estimation of the International Space Station, fuel tank cost will be around 5 million per each tank. We will be using ion engine which will cost around $500,000. Control module and solar panels will cost around $10 million. Fuel used here is xenon gas which will cost $10 per liter. On basis of estimation of module in International Space Station, fuel tank $5 million per tank, all affect ion engines $5,000 per engine, power management plus solar power 10 million per system. Fuel used is xenon gas which cost about $10 per liter. Thank you.
Hi, this is Jayant again, and I will be giving the brief detail of the solution. A spinning space module with a long cable will dock into the incoming space vehicle and start to rotate and then launch the vehicle into the required direction. By this method, the vehicle gains the desired velocity for interplanetary missions without the use of an extra fuel. By doing so, we can reduce the travel time in between missions and also the fuel consumption of rockets, and hence increases the useful payload quantity. In a similar manner, we can have another tether to catch and slow down the incoming vehicle to land on the target or back to Earth. And by using such tethers, we can use refuel incoming spacecrafts if required. Current space travel to Mars takes around 9 months. This time can be reduced to 3-5 months with the use of spinning space tether. Reduces fuel for interplanetary travel. Now, our approach to this current issue of rocket industry is relatively simple than what many people claim. So, our approach of solution for a lunar mission or an interplanetary mission to Mars, the spacecraft which has been sent to the orbit of Earth shall dock itself to our proposed space tether and then will refuel itself. Later, the system will start spinning to give the spacecraft a centrifugal velocity in the desired orbital plane for its journey. Ways to spin the tether. Using the engines on tether to get the torque to spin, using Earth's magnetic field by passing electricity in tether to get appropriate torque. The flow of operations has been shown on the screen. First, spacecraft docks into tether, then tether starts to spin, then spacecraft undocks at calculated moment towards the required trajectory. Interstellar travel of spacecraft, then spacecraft is caught by target tether and speed is reduced. Then finally, spacecraft thrown to a target planet or moon to land. Now, performance estimate. Assuming that while docking the tether can be kept stationary relative to approaching spacecraft in a considerable range by the computer in craft and tether on board, it is safe to assume with this method more than 90% of interplanetary mission will be carried out by method as it saves on time and fuel. Again, no real world data available for this. To conclude our presentation, we'll now be showing our simulation. As you can see, our tether is holding on to the satellite and spinning. And now you will see the launch of the satellite. As you can see in the video, the satellite is thrown. Now we will be showing the animation of this simulation.